All right, this is video 26 to the baby girl analysis series. So a function is called Lipschitz. I'm not sure if I'm pronouncing that right, but click Lipschitz. But a function is called Lipschitz if over A, if and only if there exists some positive number k, such that for all x and y in A, we have that the absolute value of f of x minus f of y is less than or equal to k times the absolute value of x minus y. So that's what it means for a function to be Lipschitz. A theorem, if f is Lipschitz, then f is uniformly continuous. And the proof of this is pretty straightforward. We're given epsilon, choose delta to be epsilon divided by k. Hence, if x minus y less than delta, then for all x and y in A, we have that the absolute value of f of x minus f of y less than or equal to k times the absolute value of x minus y. That's Lipschitz, and then that is less than k times epsilon over k, which will give you epsilon. All right, so f is Lipschitz, then it's uniformly continuous. Here's another theorem. If f is continuous over closed and bounded interval AB, then f is uniformly continuous over that interval. So did a proof by contradiction. And so by contradiction's sake, let's assume f is not uniformly continuous over the closed interval AB. So then that means there exists an epsilon for all delta. There exists x and y such that the absolute value of x minus y less than delta and absolute value of f of x minus f of y is greater than or equal to epsilon. So by letting delta equal 1 over n for all n, we're going to find sequences xn, yn in the closed interval AB, where we have the absolute value of x minus y less than 1 over n, and the absolute value of f of x minus f of y is greater than or equal to epsilon. So we're assuming it's not uniformly continuous, so find these two sequences, xn and yn, that has this property of it for it not being uniformly continuous. Well, since sequence xn is a subset of the closed interval AB, then by the Bolzano-Weierstrass theorem, there exists a convergent subsequence. And let's say the convergent subsequence is xn k. And since it converges, let's say it converges to some value x. Now this value x is also part of is an element of the closed interval AB, because the closed interval AB is, well, it's closed and bounded. So we need to choose a subsequence y and k of the sequence yn so that the indices match. And in this case, we could say that we have f of x and k minus f of y and k, that itself is a subset of the sequence f of xn minus f of yn, which would then imply that y and k converges to x also. All right, so the claim is that y and k converges to x. So the proof of this claim, given any delta, the absolute value of y and k minus x is equal to the absolute value of y and k minus x and k plus x and k minus x. So we're adding 0 in the form of minus x and k and plus x and k. So by triangle inequality, that's less than or equal to the absolute value of y and k minus x and k plus the absolute value of x and k minus x. So the first absolute value, where it's y and k minus x and k, that's going to be less than less than a y 1 over nk. And that we need that to be less than delta over 2. And so we know by Archimedean principle, there's going to be some natural number, so that natural number will be less than delta over 2. And so we assumed that it was not uniformly continuous. So for the sequences x and y, and we had that the difference of x minus y is less than 1 over n for all n. So then the difference between y and k, absolute value of the difference between y and k and x and k is going to be less than 1 over nk, which would be less than delta over 2 by the Archimedean principle. Since x and k converges to x, then we can choose capital N such that the absolute value of x and k minus x is less than delta over 2 for nk bigger than capital N. Now we need to make sure this capital N is such that we have 1 over capital N less than delta over 2. So then for nk greater than capital N, 1 over nk is less than 1 over capital N, which is less than delta over 2. Then we have that the absolute value of y and k less than or equal to the absolute value of y and k minus x and k plus the absolute value of x and k minus x is less than delta over 2 plus delta over 2, which is equal to delta for any delta. So that means we've shown that this subsequence y and k also converges to x. So by continuity of f over the closed interval a, b, we have f of x and k converges to f of x, and f of y and k converges to f of x. Hence, the difference of f of x and k minus f of y and k converges to f of x minus f of x, which is 0. But this is a contradiction since the absolute value of f of x minus f of y needs to be greater than or equal to epsilon. All right, so that completes the proof. It was a contradiction proof. And that was proving that if f is continuous over the closed interval AB, then f is uniformly continuous. Now the next thing is dealing with Cauchy. If f is uniformly continuous over A and xn is a Cauchy sequence in A, then f of xn is also Cauchy in the reals. So for Cauchy, we need to show that for all epsilon, there exists a capital N. So for all little m bigger than little m, which is bigger than capital N, we have that the absolute value of f of xm minus f of xn is less than epsilon. All right, so that's what we need to show, and we need to use the fact that we know f is uniformly continuous and that xn is Cauchy. So given epsilon, since f is uniformly continuous over A, then there exists a delta for all x and y in A. We have that the absolute value of x minus y less than delta implies that the absolute value of f of x minus f of y is less than epsilon. So the sequence xn is Cauchy. So let capital N be such that for all little m bigger than little n, which is bigger than capital N, the absolute value of xm minus xn is less than delta. So with this choice of delta, we have for little m bigger than capital N, that the distance of xm minus xn is less than delta will imply that the distance of f of xm minus f of xn is less than epsilon. So therefore, f of xn is Cauchy. All right, so that's that theorem. And we're going to use this along with maybe one of the previous theorems to prove this theorem. So let f be continuous over an open interval AB. F is uniformly continuous over AB if and only if f can be extended to a continuous function over the closed interval AB. All right, so the proof So this backwards direction, I'll do that first. So if f can be defined, so as an extended continuous function, so that means if f can be defined to be continuous at the endpoint A and the endpoint B, well then, we know then if that's the case, then f is continuous over the closed interval AB. And we showed that earlier that if f is continuous over the closed interval AB, then f is uniformly continuous over that closed interval AB. So by previous theorem, it's uniformly continuous. Okay, and so if it's uniformly continuous over the closed interval AB, then it's going to be f is uniformly continuous over the open interval. Since that's a subset of the closed interval. All right, so that direction's pretty straightforward. It's the other direction that's going to take a good bit of thinking, I guess. So the other direction I'll do over here. So we're going to assume f is uniformly continuous. And over the open interval AB. And then we need to show that f can be extended to a continuous function. All right, that's what we need to show. So this is a sketch of the idea. Now, if we have some interval AB, open interval AB, if we have a sequence xn that converges to B, so some sequence xn converges to B, then since it converges, we know the sequence xn is Cauchy. And since, so that's going to be, means f of xn is Cauchy. So that means f of xn converges, and let's say converges to some value L. And then if then we need so that L equals f of b. That just shows that that limit is equal to that. We still have to show the function is continuous. And we need to also, let's see, we probably need to, and to show that it's continuous, that means we need another sequence yn converges to b. And so f of yn needs to converge to b. All right, that's going to be the idea that we're going to be implementing. So we're going to use the fact, okay, so f is uniformly continuous over AB, and we need to show it can be extended to a continuous function over the closed interval AB. So let's say we focus on the endpoint B, and so then if there's going to be a sequence xn that converges to B, that means xn is Cauchy, and then f of xn is Cauchy. So then that means it converges. Then f of xn converges to L, and that's equal to f of b, but we still need to show f is continuous, so we have to choose another sequence yn that converges to b, and show that that f of yn converges to f of b. And that would be meaning it's continuous. Okay, so let's go into the proof. So we already assume f is uniformly continuous over AB. We need to show that it can be extended to a continuous function over the closed interval AB. Basically need to show it's continuous at A and continuous at B. And meaning it's got to be defined at A and defined at B. Okay, so let's start with B. So let the sequence xn be a subset of open interval AB, where xn converges to B. And so that means the sequence xn is Cauchy. And then that will imply that f of xn is Cauchy. All right, that was one of our theorems from earlier. All right, this theorem, if f is uniformly continuous over set A and xn is Cauchy in A, then f of xn is Cauchy in the reals. So f of xn is Cauchy, which means it converges, since every Cauchy sequence converges. Let me go back to the proof. So f of x in converges, let's say it converges to the value L. So that's since Cauchy sequences converge. Now define f of b to equal L. Now let the sequence Yn be a subset of AB where Yn converges to B. We need to show that f of Yn also converges to L. And this will demonstrate that f is continuous at B. All right, so that's what we need to do. All right, so the proof is so far what we've written. F is uniformly continuous over open interval AB. We need to show that f can be extended to a continuous function over the closed interval AB. Which means we need to show that it's continuous at A, continuous at B, meaning it's defined at A and defined at B. Start with the endpoint B. Let xn be a subset or a sequence in AB, and where xn converges to B. Since xn converges to B, it's Cauchy, since every Cauchy sequence converges. And then f of xn is going to be Cauchy by previous theorem that we went over in the video. And since f of xn is Cauchy, then f of xn converges to some value L. Define f of b to equal this value L. Let Yn be a sequence in AB where Yn converges to B. We need to show that f of Yn also converges to L. And that will demonstrate that f is continuous at B. All right, so that's what we've done so far. You know, by sequential criterion, for continuity, we basically need that for given epsilon, we need to find a capital N such that for n bigger than capital N, the absolute value of f of Yn minus L is less than epsilon. Okay, so, well, if we have this absolute value of f of Yn minus L, that's equal to absolute value of f of Yn minus f of xn plus f of xn minus L. So we're just adding 0. Okay, and by triangle inequality, this is less than or equal to f of Yn minus f of xn plus the absolute value of f of xn minus L. Okay, so we need all of that to be less than epsilon. So what can we do? All right, so we essentially need to find a delta so that this is going to be less than epsilon over 2. And then this needs to be also less than epsilon over 2. So the blue is sort of just my thought process. Okay, so how do we get this epsilon over 2? Now, if we have, we need to find delta. Such that x minus y is less than delta. Then we have the absolute value of f of, when we do y minus x, so it's in the same format. So y minus delta, or y minus x less than delta. So f of y minus f of x is less than, let's say, epsilon over 2. All right, so how do we do this? And for sequences yn and xn, so if we have the absolute value of yn minus xn, that's equal to, and we know we're having each one of these converge to b, so that's equal to yn minus b plus b minus xn. And that's just adding 0 in the form of negative b and plus b. And that's less than or equal to yn minus b plus the absolute value of b minus xn. And we need this to be itself less than delta over 2. And then this to be less than delta over 2, or delta divided by 2. So that's the absolute value of yn minus xn be less than delta. We need to find the indices so that this happens. So we need to find n1 for this one by using the fact that yn converges to b, and we need to find an n2 for this one, since we know xn converges to b. And if that's the case, then we could have this epsilon over 2. Now we also need a third capital N, where we know so that f of xn minus L is less than epsilon over 2. Okay, so then we need a third N, and I'll use orange. Let's call it N3, so that we have f of xn minus L less than epsilon over 2. So these n1 and n2 correspond so that we have f of yn minus f of xn to be less than epsilon over 2. And we need a third value, n3, to correspond with having f of xn minus L less than epsilon over 2. And we are using the fact that f of yn minus f of xn that can be made less than epsilon over 2, since yn minus xn adding negative b plus b, we use the fact that yn converges to b, xn converges to b to find an n1 so that we have the absolute value of yn minus b less than delta over 2, and then the absolute value of b minus xn less than some delta over 2 for n2. So then that's getting arbitrarily close. So then that would give us a f of yn minus f of xn to be less than epsilon over 2. And we're going to base it off the fact that we know that f is uniformly continuous. All right, so I know it's kind of a lot of going on here. So let me sort of make it a little bit more formal now. So given any sequence yn in A, B, where yn converges to B, since f is uniformly continuous over AB, then given any epsilon, let delta be such that if the absolute value of y minus x is less than delta, then the absolute value of f of y minus f of x is less than epsilon over 2. All right, just using the fact that it's uniformly continuous. So let n1 be such that if little n is bigger than n1, then we have that yn minus b is less than delta over 2. Let n2 be such that if little n is bigger than n2, then the absolute value of xn minus b is less than delta over 2. And then let n3, I think I used orange, yeah, so let n3 be such that if little n is bigger than n3, then the f of xn minus L is less than epsilon over 2. So choose n to be the max. Of n1, n2, and n3. Then for little n bigger than capital N, we have the absolute value of xn minus yn, which is less than or equal to the absolute value of xn minus b, plus the absolute value of b minus yn. And that's less than delta, plus delta divided by 2, plus delta divided by 2, which is delta. So xn minus yn is less than delta. So absolute value of f of xn minus f of yn less than epsilon over 2. And then we have the absolute value of f of xn minus L less than epsilon over 2. And therefore, we have hence the absolute value of f of yn minus L is less than or equal to f of yn minus f of xn plus the absolute value of f of xn minus L and then that's less than epsilon over 2 plus epsilon over 2. So that's epsilon. And so that means f of yn converges to L if and only if the sequence yn converges to B. Because L is equal to f of B. All right, and doing the other endpoint is handled pretty much the same. So do the similar process for the other endpoint A. All right, so then that means f can be extended to a continuous function over AB. All right, so that completes the proof. Okay, so that was fairly involved. Just read through it. Now I kind of put in some ideas in the middle of that proof, but this forward direction was assuming f is uniformly continuous and needed to show f can be extended to a continuous function, which means you need to show that f is continuous at A and continuous at B, or it needs to be defined at A and defined at B. So we started with, we only handled endpoint B, but endpoint A is handled pretty much the same. But if for endpoint B, let xn be a sequence where xn converges to B. Since it converges to B, xn is Cauchy. And then that means f of xn is Cauchy by a previous theorem. So since it's Cauchy, f of xn converges to some value L. Define f of b to equal L. So let yn be a sequence in AB such that yn converges to B. We need to show that f of yn converges to L. This will demonstrate f is continuous at B. So by sequential criterion for continuity, for all epsilon, we need to find in capital N so that for all little n bigger than capital N, we have that the absolute value of f of yn minus L is less than epsilon. And so that difference, f of yn minus L, can be broken up so that using the triangle inequality, it's less than or equal to f of yn minus f of xn plus f of xn minus L. And so if we needed to get each one of these two to be less than epsilon over 2. And to do that, focusing on just the first one to make it less than epsilon over 2, we need to find a delta. So if y minus x is less than delta, f of y minus f of x is less than epsilon over 2. So for our sake, we're dealing with sequences yn and xn. And so we needed that difference of yn minus xn to be less than delta. And that involved using the convergence of yn converges to b and xn converges to b. So we found an n1 and an n2 based on those, where we had yn minus b less than delta over 2, and then b minus xn less than delta over 2. So when we add it together, we get delta. Now that was for f of yn minus f of xn to be less than epsilon over 2. Then we needed to take care of the f of xn minus capital L. Well, we've already said that f of xn converges to L, so find an n3 so that f of xn minus L is less than epsilon over 2. All right, that was the thought process, and then I sort of just made it a little bit more formal down here and said given any sequence yn and ab where yn converges to b, since f is uniformly continuous over ab, and given epsilon, let delta be such that if y minus x is less than delta, then f of y minus f of x is less than epsilon over 2. All right, so for this we found an n1, so that if n is bigger than capital N1, then yn minus b is less than delta divided by 2. We found an n2, so that if little n is bigger than capital N2, n minus b is less than delta over 2. So that way we get it to be less than delta. And then we use that f of xn converges to L, so we found an n3, so that if little n is bigger than capital N3, f of xn minus L is less than epsilon over 2. Choose n to be the max of these three n values. So for little n bigger than capital N, then the absolute value of xn minus yn, we broke that up by triangle inequality and adding 0 in the form of b. So it's xn minus b plus b minus yn. And each one of those is going to be less than delta divided by 2. So the delta over 2 plus delta over 2 is delta. So then we have xn minus yn less than delta. And for that delta, we get that f of xn minus f of yn is less than epsilon over 2. And then we get that f of xn minus L is less than epsilon over 2 for the n. If n is bigger than capital N, if capital N is the maximum of n1, n2, and n3. So hence f of yn minus L less than or equal to f of yn minus f of xn plus f of xn minus L. Each one of these is less than epsilon over 2. So then we get epsilon. So that means f of yn converges to L if and only if yn, or f of yn converges to L if and only if yn converges to b, since we have L equal to f of b. And then you do a similar process for the other endpoint A. So that's where I'll stop the video.